Thank you for playing the video. My name is Zhening and I'm presenting our work, Rethinking Color Precision. We introduce a real-time perceptual spatial quantization for foveated graphics that reduces the peripheral color precision. We designed a two-step workflow and propose a step mask based on the user study, achieving more than 80% of data redaction during transmission theoretically. So pay attention to the outermost region in this scene. The color precision is reduced to 3 bits per pixel, and it is hard to notice the difference within gaze contingent near-eye display. So to start with, I want to give a little bit background on how uneven our human visual system is. A simple way to picture a visual angle is to stretch your hand at the arm's length and hold your 3 fingers like this. And these 3 fingers covers roughly 5 degrees of your visual field. And if you fixate on the center of this region, only the central part is seen at highest acuity, and everything further away would be slightly precise, or to say a little bit blurry. The central region is called the fovea, and everything outside it is the peripheral vision, or the periphery. Retinal eccentricity is the angular distance from your gaze point. And as you can see in this image, when retinal eccentricity increases, the numbers of your cone drops significantly. And this contributes to the reduced visual performance, especially in the periphery. It is important to understand the peripheral vision because it covers a large portion of our visual field. And it also helps us understand where the visual detail matters and which visual tasks are more important and easier or difficult for us to perform. From a practical perspective, this is especially relevant to near-eye displays or XR headsets. And XR headsets requires very high resolution because their pixels are placed around with very wide field of view and magnified by the optics, and they are placed at very close to your eyes. At the same time, the requirements of refresh rate is also very high for users to avoid the motion sickness. So together, these requirements create a bandwidth challenge for rendering and streaming. And the non-uniform nature of our visual system has inspired the foveated graphics. And this includes imaging, rendering, and streaming. And based on the drop-off in visual acuity, the foveated methods reduce the quality or spatial resolution in the periphery to accelerate the rendering or transmission. As you can see in this image, they separate it into 3 layers with different spatial resolution. Similar to visual acuity, our color perception also drops significantly as retinal eccentricity increases. An important point to know is that our color vision does not disappear. We can still see color, especially when we pay attention to the periphery. Previous studies have shown that the color is reduced, for example, through the color discrimination. And in this study, you can see on the left-hand side and the right-hand side is the fovea and the periphery. And these eclipses means the set of color that people cannot tell apart from. It increases significantly when it's in the far periphery. And a more recent study shows that the chromatic resolution can drop even faster than achromatic resolution. So this means we might be able to save more considering the peripheral vision for colors. So we know that most foveated graphics methods exploit the spatial resolution. And since we learned that our color perception is not also uneven, but like normal rendering pipelines, the color values are still allocated uniformly across the whole visual field. So here comes the question. Given that this is reduced in the periphery, can we imperceptibly reduce the peripheral color, representation or color bandwidth? Before this paper, there was already work exploring gaze contingent color reduction for bandwidth saving, either by reducing the saturation or hue resolution. So for example, the desaturation, you can think about it as reducing the color channels to only gray or black and white. And this is still noticeable as we know. And for hue resolution reduction, previous studies have done this through reducing the bit depth for each channel, either in RGB or LAB color space. And this can cause hue shifts, banding, and false contours, as you can see here very obviously in the sky. And these artifacts are still very visible, even if it's in the very far periphery. So the key idea of our paper is to move from per pixel color position to spatial color perception. If each pixel is reduced directly to the lower bit depth color in the sparse color palette or sparse color space, the arrows would often become structured. As you can see, from 3 to 1 bit, it becomes very obvious. And these structures are still perceptible in the periphery. Instead, we want to distribute these color arrows spatially. The way we do this is through adding dithering at the same time when we perform quantization, and the arrows will turn into high-frequency variations. And this can work because as eccentricity increases, the visual acuity drops and the pooling increases, and aggregate local statistics becomes more important than the exact location and content of each pixels. And dithering takes advantage of this by breaking the structured quantization artifacts, and these high-frequency artifacts would kind of falls below the acuity limit and be pulled together in the periphery, and hence we can see them as the color experience rather than seeing the pixels. However, as you can see here in the lower bit depth regions, and quantization can still create visible lightness shifts due to the contrast change. And to recover the lightness change, we add a blur recovery layer. By averaging the sparse neighboring colors, it also kind of acts as a dequantization step. So to summarize, this is a two-step workflow. We always keep the fovea at full fidelity, which is 8 bits per channel without any blur, and we want to drop the bit depth in the periphery. After some preliminary testing, we implement the order dithering with 8x8 Bayer matrix. For each pixel, the original value in each channel is compared against the spatial varying threshold determined by the Bayer matrix, and then the threshold compares again and assigns the pixels to one of the available quantization levels. And for recovery, we use Kawase blur, a very lightweight blur that is used in real-time graphics. So the practical application of this is to use within a standalone mobile headset. In the setup of a client-server streaming, this original frame is rendered purely on the server side. And we can add a post-processing layer in the server to lower the bit depth and hence reduce the frame size during the transmission. The system reduces data in the bit stream, which can be used to accelerate wireless streaming over the network. For example, Steam is about to release their headset, which they will be using Foveated streaming. And also, this can help save power within the mobile headset by reducing the DRAM traffic. So the next question is, how much color position can we reduce before people notice? We want to estimate the eccentricity threshold where the artifacts becomes imperceptible and build a bit allocation mask based on that. So we conduct a staircase to AFC user study with two factors, the bit depth and foveal radius, which is the retinal eccentricity. And we design a stimuli to contain different kinds of visual features that matters, and recruited 29 participants with 7 people having visual deficiencies. And we tested this within the Pimax Crystal headset, which has a built-in eye tracker and a large field of view. Based on the user study, we have the statistical results. The x-axis means we drop from 7 bits per channel to 1 bit per channel in RGB space. And when people stop noticing at certain eccentricity, we record the data. And the y-axis means the retinal eccentricity starting just right outside the fovea to the very far periphery. As shown on the right side, we build a step mask dropping from 7 bits to 1 bit per channel. In general, the higher bit depth conditions from 7 to 4 bits per channel are relatively stable across different participants and remain undetectable, meaning that the bit can drop quickly to 4 bits when it's just outside the fovea. But once the bit depth goes to 2 or 1 bit per channel, the threshold increases quickly and varies across participants. One observation is that participants mostly notice the artifacts in high-frequency regions, and they often describe these artifacts as shimmering rather than obvious color change. We calculate the potential data bandwidth saving with an area-weighted measurement. Assuming the gaze at the center, the mean threshold gives an average bandwidth of about 4 bits per pixel, compared to the standard 24 bits per pixel color representation in RGB. It saves more than 80% of data. So for example, with the Pimax crystal configuration, it reduces the raw frame size from 24 megabytes to 8 megabytes. We also consider a safer transition zone to balance the quality and saving. In the worst case, the bandwidth is still about 7 bits per pixel, which gives us around 70% of reduction. This method is also very lightweight. The Unity post-processing implementation takes about 10 microseconds for spatial quantization and 20 microseconds for the blur per frame. This is a full HD capture. You can kind of imagine how the masks works compared to the original ground truth. But the actual effect would be more realistic when it comes to the headset. We capture the frame from Pimax crystal. As you can see on the left-hand side, the moving white dot is the current gaze point. And on the right-hand side, this is the zoom-in view of the far periphery, which only has 1 bit per channel or 3 bits per pixel. And we also compare it with the ground truth. And the foveated frame might be obvious when it comes to like the screen that is currently being displayed, but it actually works quite well within the headset. So there are several directions for future work. The first, the natural next step would be jointly optimize this with spatial resolution, which might give us more saving. And second, the current method uses a relatively fixed image-independent quantization. For future work, we could try to select palettes smartly based on the frame content, the gaze position, and eccentricity. And finally, the method could be integrated with practical streaming or video encoding pipeline, so we can test it how it actually performs in real like codecs or end-to-end video streaming systems for VR. To summarize, the main contribution of this paper is to show that color reduction can be done within foveation systems. And we designed a two-step workflow to reduce the color bandwidth for rendered frames. We proved its feasibility through a user study and made a drop-off mask and also a transition zone that kind of help us balance the compression rate and the quality. And this is the reference list. And this is our product page. Yeah, thank you very much.
So we do have the author online to answer questions. So if you have any questions, feel free to ask. I'll start off with one then. So with this foveation and changing the bit depth, what's the thing that you first notice as this degrades enough that it starts to become perceptual? Is it the transitions between the bit depth, or what's sort of the failure case of this if you increase the quantization too much?
Yeah, thank you for asking. This is a very interesting question because we first tested this mask only on the dithering part, and the most noticeable thing is the transition zone because we have like the lightness shift, so you'll see the things getting a little bit like brighter or brighter, or like precisely like whiter and whiter when it comes to lower bit depths. And this is why we add the recovery blur. So it kind of removes the edges when it comes to the transition zone. And for the final part, so we have the final mask that comes something that when it comes to high frequency areas and we do the dithering and then the blur, there will be some things look like downsampling artifacts when it comes to high frequency areas, because you know that we can't preserve these high frequencies when it's reduced, especially using like dithering.
All right, thank you. We do have a question.
I saw some work on using a base plus offset in a similar kind of foveated way to this, and I wondered how your work compares to that work, and also he, in the presentation, compared it to PNG compression, and I wondered if, it seemed like his in some cases was better than PNG, which is an offline method, and it surprised me and I thought it was cool. I wondered if your method had similar compression to that, or how it compared.
So you mean the base and delta method?
Yes.
So this would be something, thank you for asking. And this would be something we would consider in the future, because as you think about it, if you do the dithering, it will be very difficult to kind of compress it spatially. So we were thinking of different methods if we can kind of restructure these dithering instead of just using the Bayer matrix to make it more compressible, or to say like easier for codecs to make use of them. And that would be something we will do in the future.
Okay, thank you.
Thank you.
Thanks for the great presentation. If I understood correctly, the system you have is a post-process on an already rendered image. And I was wondering, in terms of integration, if you want to have less expensive shading on the areas that will have lower bit depth, if that's something that's doable. Like how would you design a system where you can just spend less time in your shaders if the results are going to get compressed at the ends anyway?
Yeah, thank you for this question. This is something we want to do, like really want to do in the future. Like current things that is regarding the color foveation are still mostly on like transmission and streaming, because it's not very direct how we can use this in like to accelerate the rendering. But if we think about it, we might be using this with, for example, compressing the texture, or like do something with the material when it comes to the periphery. And we're still like trying to work on this part.
Okay, thank you.
Other questions? All right, if not, let's thank our speaker again. Thank you.